Hello everybody, today we're going to be talking about maximum minimum values, the extreme value theorem, and Fermat's theorem. So this video is just going to be an overview of these three things. We're not going to do any problems. In the next video, I'm going to do problems where we find critical points, max, min values inside of an interval and then outside of an interval. So let's jump right into it. So maximum minimum values. So these, I have definitions in here, and these are pulled directly from Cengage's textbook. So, try to follow along because the English is not plain English. I'm going to try my best to summarize it in plain English. So our first definition for maximum minimum values says, let C be a number in the domain D of a function f, then f of C is the either absolute maximum value of f on D or absolute minimum value of f on D. So in plain English, what I believe that this is saying is you're going to have a number. This is going to be a critical number. This critical number must lie within the domain of your function. C is represented as your critical number or critical point. Now, what is a critical point? Well, in calculus, a critical point of a function is a point where the function's derivative is either 0 or is undefined, and we're going to talk about that a lot more later when we're talking about Fermat's theorem. But for right now, I just need you to understand that a critical point or value, indicates potential local max, min values, or absolute max, min values. So what is an absolute max and min value anyways? So let's take a look at this example. Example 1. In this example, just by looking at it, we can tell that this is our absolute maximum value because that's the highest point in this function, right? So here would be our absolute max. And then where's our absolute minimum? It's down here. And it's the absolute min and max because we have these closed circles or closed points that indicate that this is an interval. So if we were to write the domain of this function, let's say this is 1, 2, 3, 4, 5, 6, 7, then our interval, our interval would be 1 and 7 because that's our x values, right? This is how long our function is. It goes from 1 to 7, and that is it. So because we have a closed interval, this is our absolute max and our absolute min because there's no other parts of this function. This is all the function is. So in our interval 1 through 7, we are actually told that these are endpoints. These are both endpoints. Now, sometimes they can be your absolute max, sometimes they could be your absolute min. Now, let's take a look at an example where we actually have a condition where our absolute max is our endpoint. So let's draw a little graph real quick. And I'm going to clean this up a little bit, I think. Actually, I'll just zoom in. So, here. Let's just draw a random graph. It really does not matter. It really doesn't. I just need you to understand this. And where did my blue go? Okay, here we go. So, let's say, and again, this is a closed interval example. So we have a function like this, right? Again, this is a closed interval because we have our points that are colored in. So, in this case, our highest point in this entire function is right here. And that's our endpoint. So sometimes inside a closed intervals function, your endpoint can be your max and sometimes it can be your minimum. In this example, this is our absolute max. This right here is our absolute minimum. And this would be called our local max. All right? So I hope that makes sense. And in regards to critical points, this and this would be your critical points. And again, we're going to talk more about that in a little bit, but I just want you to get a visualization of it. So remember, your critical points help you figure out where your max and mins are. So let's do another example where we aren't in an interval. So let's close this out. Okay, let's draw something else. All right, we have another graph. Okay, so she is going from negative infinity and she's climbing all the way up, and then she's gonna stop right here. So we have a partial interval. So our domain would be negative infinity to, let's say this is 10. So this would be our domain for this function. It'd be going from negative infinity to 10, and that's where it stops. So only this point is inclusive. Okay, so that means that we have an absolute maximum right here. Again, that is also our critical point. So this is our absolute max. This would be our local min right here. That point would be our local min. And then we don't have an absolute minimum because it just keeps going down and down and down forever and ever and ever, infinitely, right? So we can't say that it has an absolute minimum. So in this problem, we only have an absolute maximum and a local minimum, and that is it. That is all we have. So I'm hoping this is making sense. Now we're going to move on to ones with conditions where we either have one or we don't have either. And something I just want to note, because when I first learned this, people in like textbooks would use jargon that I simply do not understand. So I just want to make something clear and make a note of. Absolute maximum and minimums are also called global max and mins. So if you're asked to find what's the global max and min of this graph, okay, it's just asking for the absolute max and min. I don't know why they make things so complicated, but I hope that helps a little bit. And then also, the max and min values of a function are called extreme values of a function, or of f, okay? So extreme values are literally just your max and min values, all right? So let's take a look at an example where we only have one. So kind of similar to the other one, but an opposite this time. We have a absolute minimum at 0. That is an absolute min. However, we do not have an absolute maximum because, again, this goes on infinitely, forever and ever, okay? Like our domain, I mean, our x domain is literally negative infinity to infinity, right? And then our domain of y is inclusive 0 to infinity. So here we have an absolute minimum value, but we don't have an absolute maximum value or local minimums or local maxes. That's all we have is an absolute minimum. So let's take a look at this next example. Y equals x to the third power. When graphed, it looks something like this, right? And if we look, we actually don't have either. We can't have a max or a minimum value, or absolute max or minimum value in this function, because our minimum goes on forever and ever in a negative direction, and our absolute maximum goes in a positive direction forever and ever. So therefore, there's neither, nor is there local max or min. So our next definition from the textbook is this. Again, don't hate me. I'm just the messenger. Like, this might be important to you or it might not. So here's the textbook jargon, all right? The number f of c is a local maximum value of f if f of c is greater than f of x when x is near c. And then the number f of c is a local minimum value of f if f of c is less than f of x when x is near c. This is basically just helping you figure out, oh, what are the parameters when x is near c that tells us that it's a maximum value and a minimum value. But again, if you're looking at it graphically, I feel like it's pretty freaking obvious what your absolute max and min is. And then when you solve it algebraically, which I will be doing in the next video, you have tests in place that literally tell you it straight up. So I feel like this definition is a little useless, a little bit. So let's get into the extreme value theorem. So this is our direct definition. So again, do not shoot the messenger. Let me erase this. I don't know what this is. So it says if f is continuous on a closed interval AB, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in A and B. So what does that even mean? Like, I was reading the textbook and I was wondering to myself, do they really think we're reading this and we're thinking, yeah, that makes sense? No, what does that even mean? Okay, anyways, sorry for that rant. But this is saying in plain English, because they just make everything so difficult. What this is just saying is, hey, you have a function, it's an interval, right? It's inclusive on both sides, A to B, which is what it says right there with those brackets. It's continuous. Great! Then that means you will have an absolute maximum and minimum value. You're gonna have it, period. So let's take a look at example 1. So what does it even mean by continuous? Let's see if it even falls within the parameters of the extreme value theorem. Continuous means there's no breaks or jumps. So let's see. If you can take your finger and you can go all along this graph, well, I guess function, and you don't have to jump or break the line you're making or curve you're making with your finger, then it's continuous. That's what it means. All right, it's all one thing. All right, so it fits the parameter of being continuous. Now, is it in a closed interval? Yes, it is, right? We have these closed points. That's telling us that this is in a closed interval. Great. Then that means that the extreme value theorem applies to this function. And all it's telling us is, hey, it fits these parameters, so you're going to have an absolute maximum and you're going to have an absolute minimum value. So, again, just by looking at the graph, you can just tell. Like, you can just tell. This is our absolute max. And this little point would be our critical point, right? Because that helps us identify maxes and mins. And then this guy would be our absolute min. And this point right here would be our critical value at that point. So we have an absolute max and absolute min. So what is it even talking about in this last part? An absolute, it's either going to have a maximum or minimum value FD at some points, at some numbers or points C and D and A and B. So what does that even mean? So basically it's saying, hey, between A and B, you're going to have a max and a min, right? And those could be labeled as C and D. So here at point C, we have an absolute max. And then at point D, we have an absolute min. So that's just all it's talking about. Like, so complicated for no reason. So let's take a look at example 2. Again, does it fit the parameters? Is it continuous? Yes, it is continuous. It has no breaks or jumps. Perfect. Now go to the second part. Is it in a closed interval? Yes, it is. We have those closed circles, which indicate that it is an interval. Okay, those are inclusive points. So we're going to have an absolute maximum and absolute minimum. So where is that going to be? And in this example, our absolute maximum is somewhere here, somewhere around there. So that is our absolute max. And then our absolute min is actually going to be our endpoint. Absolute minimum, in this case, is our endpoint. And then again, if you really wanted to include like C or D, boom, you can do that right here, where you have this somewhere, it's going to lie around here. So that would be like your C, okay? And then, pause the video and try this one out. This one's pretty cool. So let's see if it fits the parameters once more. Is it continuous? Yes. Is that in a closed interval? Yes. Okay, then that means we're going to have absolute max and absolute minimum. So what is our absolute max? Well, if you look closely, we can create a line like this, right? So that means that we have 2. They touch the same exact high point. So we have 2 absolute maxes. It's the same thing, right? It's the same y value. So we have 2 absolute maxes at this point and at this point. So we have 2 critical values here. And then we have 1. Actually, we have 2. We have 2 absolute minimums as well. So you can have more than 1 if it's at the same point. All right, so let's move on to some examples that don't fit the extreme value theorem's parameters. So if we look at example 4, we do not have a continuous function. she breaks, right? She's not continuous. We'd have to, if we're going from left to right, we'd have to lift up our finger so we could keep going with this function. So therefore, it already does not fit it. Also, it is not an interval. So therefore, the extreme value theorem does not apply. So if we were to look for an absolute max, we wouldn't be able to find one because this point is not colored in. Therefore, it is not inclusive. So we wouldn't have an absolute max. There'd be no absolute max. No absolute maximum value. And we would have no absolute minimum value because these points are non-inclusive, which means these go on forever and ever. So we'd have neither in this case. If we look at example 5 and we look at our parameters for the extreme value theorem, we can see that our function is actually continuous, right? We don't have to pick up our finger. So it looks like we have an inclusive point right here because it's colored in, but then it goes on infinitely, forever. So that means that our absolute minimum would be this. But again, does it fit inside of a closed interval? No, it doesn't. So it does not fall within the extreme value theorem. And we can see that because there's no absolute max. No absolute max because it goes on and on forever. So these two examples, number 4 and number 5, do not fit the parameters required for the extreme value theorem. And it proves it because, look, in example 4, we don't have either. And then in example 5, we have an absolute minimum, but we have no absolute maximum because the right side of our function is not inside of the interval. Only the left side is. And the interval for function 5 would look like this. It would look something like from 0 to infinity, right? And because we have a parenthesis instead of a bracket, that means that it is not inclusive and it's just not going to fall within the parameters of the extreme value theorem. So let's move on to another topic. So this next topic is Fermat's theorem. So what in the world? Okay. So Fermat's theorem, again, it's from the textbook, don't hate me. If f has a local maximum or minimum at c, and if f of c exists, then f of c equals 0. So what is that even saying, right? And then we also, now finally it tells us that c is a critical number of a function's domain such that either f prime of c equals 0 or f prime of c equals does not exist. And it's so funny that the textbook had you go through all these things, and until you reach this point, they're like, okay, I think now we should tell you what c is. But anyways, I digress. So Fermat's theorem states that you're going to have critical numbers only inside of the domain of your function. Therefore, if you have critical numbers that fall outside the domain of your function, they're not critical numbers. Okay? So, when finding your critical numbers inside of your function's domain, those critical points or numbers are either going to equal f prime of c equals 0 or f prime of c equals does not exist. So what the heck is that even talking about? What do you mean it's going to equal 0? So what it's talking about, if we look at example 1, and I'm going to have to zoom in a lot here so you can understand what we're freaking talking about. So if this hurts your brain, I'm sorry. So let's look at example 1. We just have a random function, okay? So it's saying at our critical points, and again, our critical points help identify our maxes and mins. So here, that's our max, and actually it's our absolute max. And then down here, we have an absolute minimum. So therefore, our critical points are here and here, okay? So what is Fermat's theorem even talking about? What do you mean it equals 0 or doesn't exist? It doesn't make any sense. So let's look deeply and really think about this. So if we're looking, again, I'm going to scroll in, I'm so sorry. So if we're looking at a function, at this point of this function, we're increasing, right? We're increasing. We're going up, 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 like a roller coaster. But at some point on this roller coaster ride, you're going to get to the very top, the very peak. And at the very peak, your slope is 0. It's for a small moment, but you reach the point where your slope is 0. It went from increasing to stopping, and your slope is 0. Okay? And what is the derivative? A derivative is finding slope. So that's why it says f prime of c equals 0. So your derivative equals 0. Your slope equals 0 at this critical point, right? And then boom, then it starts decreasing. You start going down the roller coaster's hump, right? So that's why at this point, at this critical point, our derivative is 0. I hope that makes sense in your brain. So now that we're going down this roller coaster ride, we reach the sky. And the same thing happens, even if it's falling and going up or going up and then falling. Again, we're going down, and then we reach this point. And at this point, we are not moving. It's not moving, but we're not going up or we're not going down. We're at 0. Our slope is 0. And then we go back to increasing. So again, that's how we know that point is going to equal to 0. But what helps us in addition to that? Well, in addition to that roller coaster concept, you could also think of it, well, it's honestly just a trick, not even to think of it as. At these points, you can just ask yourself, hey, can I make a horizontal tangent line at these critical points? And would you look at that? We can. If you can make a horizontal tangent line, then that is also an indicator that your derivative is going to equal 0 at those critical points. So again, if you can make a horizontal tangent line at your critical points, then that means that your slope at those 2 points is equal to 0. Now, what about when an equals does not exist? What does that even mean? Can it still even be a critical point? So let's take a look at this graph. So this graph is a continuous graph and there's no intervals. This graph was intervals, this one does not. Okay, so let's see. We can use our little roller coaster theory thing, or we can just make a horizontal tangent line. So now that you have the idea in your head, let's see, can we make a horizontal tangent line? Yes, we can. At that top point, which is our absolute maximum, aka a critical point, we can make a horizontal tangent line. Therefore, at that point, our derivative is equal to 0. So absolute max and f prime of c equals 0. Our derivative equals 0. Now, what about this guy? Does it still fall? Like how we were talking about? Like, what are even the parameters for this guy? This looks nothing like a curve, and we can't make a horizontal tangent line. So that's when it does not exist. Oops, cut. Okay, so something that you need to ask yourself is, can you make a horizontal tangent line? Well, yeah, technically you can, but you're gonna make a bunch. You can make a bunch at this point. You can't make one unique horizontal tangent line. Also, is it sharp? Is it a sharp turning point? Is it a cusp almost? And yes, it's very sharp. So therefore, at this point, at this critical point, which is our absolute minimum, f prime of c equals does not exist. So I hope that makes sense. And again, a quick recap. Your critical values are only critical values if they fall within the domain of your function. Okay? At those critical values, they're either going to equal 0 or does not exist. And again, you can think of it as a roller coaster, or you can just do a horizontal tangent line. And then, of course, to figure out if it does not exist, you can ask yourself, is it a sharp turn? Can you make one unique horizontal tangent line, or can you make a bunch? Okay, so that is how you determine whether at the critical point is going to equal 0 or if it's going to equal does not exist. All right, and then again, if you want like a stern definition from the textbook, it says if f has a local max or min at c, then c is a critical number of f. So that is all we're going to cover in this video. In the next video, I'm actually going to solve problems in which we utilize all of this information. So the next video is going to cover finding the maximum and minimum values inside of an interval, and then finding maximum and minimum values outside of an interval. and then applying, again, this information, and also finding critical points, because that's also very important. So thank you so much for watching. Have a great day.